Hi, welcome to Tech Tuesdays. I'm Michael Reis, Senior Application Engineer at Tasking. Today, I will be walking through automated errata management with the Tasking Compiler Inspector tool. By the end of this session, you will know why errata management needs to be considered in projects, how Tasking supports you in the errata management activities, and how to use the Tasking Inspector to efficiently implement errata management in your projects. Let's start with the general question: why errata management needs to be considered in safety-relevant embedded software projects. For the different domains, the relevant safety standards typically mandate errata management for software tools in case the tool has the possibility of a malfunction which can introduce errors in safety-related items or elements. Here we can see a snippet of the ISO 26262, which is the applicable safety standard for the automotive domain. It is explicitly mentioned that the description of known software tool malfunctions and the avoidance or workaround measures shall be present. Of course, when we are talking about a compiler toolset, it's very likely that a malfunction of the compiler toolset can introduce errors in the safety item or element. Therefore, you should apply errata management for the compiler toolset to ensure compliance with the applicable safety standard. This leads me to my second point. Is it possible to provide a compiler toolset, or more generally speaking, a software which is free of any malfunction, which would make the errata management obsolete? If you ask an LLM, it will probably state something similar like this: practically unachievable for real-world software. Of course, we at Tasking spend a lot of effort to provide you high quality and well-tested compiler toolchains. Nevertheless, this doesn't mean that we can guarantee the absence of any bug in it. The famous quote from Dijkstra is emphasizing this point as well. Hopefully, I was able to highlight the importance of errata management. Now let's switch the perspective and talk about how to apply errata management in your project. First of all, it's worthwhile to mention that Tasking is publishing known product issues regularly. Here you can see a screenshot of our portal, which lists the known issues with detailed information, like the impacted component and the affected toolchain. Of course, other information like a mitigation strategy, the information in which version the issue is present and in which version the issue was fixed, is available as well in the portal. As seen on the previous slide, it is the obligation from the tool user to check if the user's project is affected from such known issues and to react accordingly when required. In general, two different strategies are possible. On the one hand, you can perform these checks manually. That means you use the detailed information from the published known issue and you review the project source code manually to get an understanding if the source code is affected from a tool malfunction. Of course, a manual check causes efforts, and therefore quite often these checks are done only once in a late stage of the project. Typically, you see these kinds of different phases in projects. A manual check is often seen as part of the test or release activities. But this implies certain risks in case a tool malfunction has an impact to the project source code. If, for example, you have to modify the toolset options, or you have to use a new version or a new patch version of the compiler toolset, you typically also have to repeat parts of your test and qualification activities, which will likely cause project delays. On the other hand, you could let perform these checks automatically. This will bring several user benefits. It allows you to quickly check if a new issue reported for an older compiler toolchain version might impact the code base which is already used in the mass production software. Of course, it decreases the effort to prove that the project source code isn't affected from known issues in the used toolchain version, as mentioned earlier, a prerequisite for the safety approval. And one more benefit I want to mention here, it enables you to add such a check in your CI pipeline and to apply required mitigations like modifying the source code, updating the toolchain options, or updating to a new toolchain version or patch as early as possible in the project. Let's have a look how the tasking inspector can support you in the errata management. Probably the most important point is the way how the tasking inspector is able to detect if your source code is affected from a tool malfunction. Technically, it's based on the proven tasking compiler technology. It is enriched with so-called detectors, which are able to identify if the user source code is impacted from a known issue. As you know it from our compiler, whenever impacted user source code is identified, an inspector-specific warning is generated, which finally allows a precise defect identification and tracking. Another important feature is the capability to easily integrate the inspector in your project. As we will see in a few minutes, the way how to invoke the inspector is very similar to the invocation of the compiler toolchain itself. Therefore, it's simple to integrate the inspector into existing build systems, independent if the project is using a Windows or Linux-based host machine. Like you know it from the compiler toolchain, it's also possible to inspect only a single source file or a subset of your source files. Last but not least, the coverage of the inspector. On the one hand, the inspector is available for several tasking compiler toolset products, like the VX toolset for Tricore, which is used for Infineon RX TC2 and TC3 projects. On the other hand, it's important to mention that a high number of relevant known issues, that means issues which can introduce errors in a safety-related item or element, can be detected from the inspector. We constantly release updates with newly added detectors for feasible issues. Let's stop with the theory and start with a live demo. Just a few facts how the demo scenario looks like and the steps I will apply in my live demo. Let's assume we are working in a safety-critical embedded development project on the Infineon RX TC3, in which the tasking compiler toolchain is used. Within the project, CMake is used as build environment. To ensure safety standard compliance, we want to establish an efficient way to handle the compiler toolchain errata management. First, I will show one way how to integrate the inspector into the CMake build environment. In a second step, I will prepare the required inspector configuration. Then I will execute the inspector in this environment and will finally use an open source tool to generate an Excel report showing all the findings and combining them with the information from the known issues list from tasking. So let's start doing it. Let's quickly have a look into the existing demo project. It only uses a few C files, which are stored in the sources folder. There's one special C file with the name test.c. This C file was used to implement some code snippets for which a compiler malfunction is known. Let's have a short look. You see different functions. Each of these functions uses a code snippet which right now triggers a compiler malfunction, identified by a unique ID, which is of course linked to the tasking issue portal. The intention of this file is to showcase the capabilities of the inspector in my demo. CMake is used as a build system. we have a CMake preset JSON file, and in this CMake presets JSON file, one preset is currently defined, which is used to build the project. Now let's prepare a second preset which allows to inspect our software and source code with the tasking inspector. Let's choose the name inspect for it. To do so, I simply copy the existing preset for the compile. Of course, adjust the name. As mentioned, I will use inspect for it. Also, the results of this build will be stored in the folder inspect. From the preset configuration, the main difference is the path of the toolset we want to use. Instead of using the compiler toolchain, which is used here, I will now configuring my installation path of the inspector. I'm using the following path for my inspector installation. To complete this step, I also have to duplicate the build presets. Do this quickly. Again, simply replace compile with inspect. And we are done. Finally, we also have to create the inspect CMake file. I will simply take the compile CMake file as basis for that. In the first approach, I simply copy this file, rename it to inspect, and of course, I have to modify the binaries which are invoked. Right now, these are still the binaries from the compiler itself. So for the assembler invocation, for the linker, and for the C compiler or the control program. The binaries which are used from the inspector are simply using a prefix insp underscore. If we take a look quickly to the directory of my inspector installation, you can also see that. The folder structure is very similar to the folder structure you might know from the compiler. And in the folder ctc bin, you can see the different binaries delivered in the inspector using the prefix inspector underscore and then the normal binary name you already know from the compiler toolset. So let's simply add the prefix insp underscore to all of the binaries which are mentioned here. And now let's invoke the inspector for the first time. I will select now the new preset we have just introduced. And then let's finally inspect the project. And you can immediately see the findings of the inspector, which are reported in a similar way, like you already know it from the compiler toolchain. Let's repeat the inspect process via a task prepared in VS Code. As you can see, this task is also using a problem matcher to display the findings in the problems view. Let's pick one example. Let's take the known issue 45026. As you can see here, my test.c file is affected from this known issue. You will find an entry in our issue portal, which provides a lot of information about this issue, as we can see here. To demonstrate the inspector functionality, let's simply apply the mitigation strategy mentioned for this issue. If I scroll to the end, a mitigation strategy is mentioned, which is about disabling one of the optimization functionality. So let's disable this specific optimization option and let the inspector run again. I simply disable the optimization for this piece of code and I repeat the inspector run. As you can see, this issue isn't reported any longer for my demo project. It's important to mention that you have to invoke the inspector with the same options as you invoke the compiler toolchain. Only this will ensure that the inspector can deliver results which are applicable for your codebase. Let's spend some more time on the toolchain options, because also the inspector comes with a lot of features which can be controlled via inspector-specific options. All possible options are described in the user guide of the inspector. In the chapter 4, you will find the tool options which are sorted for the different binaries. For each option, you will find an entry which explains in detail what this option is about. Another important option is the capability to exclude issues from the analysis. For example, you update to a new patch version of the compiler in which certain issues are not applicable anymore because they are simply fixed in this patch version. The inspector offers an option which is called patch level, which will automatically exclude all the issues which aren't applicable anymore for the used compiler patch version. It is also possible to exclude issues by simply listing the issues. Again, let's check the behavior of this option. Let's introduce another variable, which is called in my example inspector flex generic, which is now applicable for the compiler, assembler, and linker. So first of all, let me put this variable to any of the options via this CMake file. As you can see, this option allows now to define a patch level. The patch level of the compiler I'm currently using in my project. Again, let's check the impact. Let the inspector run again, and we can see the number of problems which are identified is still 10. But now let's assume we have updated to a later version of the compiler. So we are using a newer patch level. So let's increase the patch level to 9. Let it run again. And now you can see the number of problems has already lowered and only 3 problems are still left. And these 3 problems are reported from a different file, so not from my test.c file. Last but not least, typically you want to process the output of the inspector in another step. So let's add an option that the inspector output shall be written into a log file. Therefore, I simply add the option insp log and I define the name of the log file. Let me switch back the patch level so that more issues are reported from the inspector. Let's run the inspector again. Of course, now we are back to 10 problems as expected. And let's also check what is now the result when we are using this inspector log option. If I go to my inspect folder where all the artifacts are stored, I can now see a log file where all the different findings are reported. As you can see, it took only a few minutes to successfully integrate the inspector in our demo project. Let's spend some more time about the post-processing of the generated data. So you can establish a connection to an Errata management workflow already used in your project by using the log file as an input. Another possibility would be to use an open source project called Inspector Log Converter, which generates an Excel report out of the log file. and combines it with the information from our issue portal. Based on the collected information in the sheet, it is easy to finally decide if there is any action required in the project. For the post-processing, with this open source tool, I have already prepared a directory with the name inspector post-processing, where I have stored the executable, which I have downloaded from the open source project. The invocation of this ilconf tool is pretty simple. Again, I have prepared a batch script which shows how this tool needs to be invoked. And I have also prepared a task simply to run this post-processing. Now you can see the ilconf tool is invoked. And after a few seconds, you will see that in the post-processing folder, an Excel sheet is generated. Let me open this Excel sheet. And then you can see we get an Excel sheet which lists all the findings in different versions. So there is a report in a compact version and a report in an extended version, where we can now see which files are affected, the information from the tasking issue portal is combined with the findings, and you get a so-called auto judgment, which tells you if this is a finding you have to take care about, or if this is a finding where with high confidence a false positive was found and therefore the finding can be ignored. That's everything I wanted to cover on the automated errata management with the tasking inspector today. Before we start with the Q&A session in a few seconds, let me close with a call for action. If you are using Tasking's compiler toolset in a safety relevant project and you want to boost your errata management, please try the inspector. We also provide evaluation licenses for that purpose. You can also reach our team at techtuesdays@tasking.com. Thank you for joining us.